All right, good morning, everybody. Sorry that I can't interact in person with everybody, but look forward to some good questions on the back end. So I'm going to start out my presentation with a video. Before I get into the video, I want to describe it a little bit. It's a excerpt of a clip from YouTube of a helicopter pilot just doing routine operations in California. He has, what I want you to notice in the video is he's not just looking out the window for obstacles. He's also responsible for listening to 3 audio channels: air-to-air, ground control, cockpit intercom. You'll also hear he's trying to figure out where he's going to land, which is pretty important. He also may not be vocalizing it, but he's also monitoring fuel available, time on target, etc., all while also manually flying the helicopter. So there's a lot of stuff going on. And for people who've seen this video before, something I noticed last night when it was on a big screen, if you look right at the beginning in this area, there's actually another helicopter that goes right by that I haven't even noticed. And I've seen this video more than once. So without further ado, try to get my laser pointer off.
All right, this is rapidly becoming very ugly.
Yeah, it is.
Echo Quebec 1, Quebec 2, 1 minute from Chatsworth. Yeah, Helco Air Tax.
All right, I got the vehicles.
Yeah, how's it looking there? That you at Castro, right?
We got the fire forward here. Could you put it down right between the fan in there and keep your rotor clear of that?
Yeah, I'm kind of looking at that right now.
Yeah, copy.
Do you see anybody?
Yeah, there's a guy with his dog.
So there's obviously a lot to be
All
absorbing.
right, this
there.
is rapidly becoming very ugly.
And if you watch the video a few times, there's actually 8 towers that are right in front of him that took me a few times to view, but he probably didn't. So really it's there to highlight that seeing vertical obstacles is not that easy. All right, my outline is going to be an introduction followed by chapter 1, which is a way to automatically detect vertical obstacles from sensor data. Chapter 2, as you saw just in the video, it's not just a matter of showing the sensor data, it's also what information matters to operators. So we're going to delve on that a little bit in the second chapter. And in the final chapter, with this obstacle information, is there a way that we can efficiently correlate it so that it can benefit future people in that airspace, and then also a way to infer the presence of power lines. My motivation is vertical obstacles, which are objects that protrude above surrounding terrain, are dangerous. Based on the sources that I show, both civilian and military operators experienced over 400 accidents, close to 300 fatalities over those time periods listed. And if you look at the photo on the right, that's an example of a vertical obstacle. If you look at it a little bit closer, you see that actually last November, there's an example of a fixed wing aircraft that ran into the tower when they were doing an approach into an airport. So it's a recent issue. Fortunately, there was no fatalities here, but obviously a lot of damage. Our goals to quickly find vertical structures in raw sensor data, then to determine what types of sensor visualization, graphic augmentation are most effective at decreasing obstacle notice time, then to efficiently consolidate vertical structure position information, and finally, finding power lines based on the vertical structure position information. The overall research approach and outline starts with what we have now, which in the upper left, this represents the obstacle files which are currently in existence. Some of those are depicted on VFR sectionals as these upside down Vs, and then basically just looking out the window for towers like you see right here. Our first chapter takes raw point clouds, and then from these raw point clouds tries to find vertical structures within those point clouds. The second chapter takes into account what these current limitations are, the current obstacle files that are available, supplements with a little bit of our ability to find obstacles within three-dimensional data, and uses that information to inform these yellow graphics that you see in the left two pictures, and also combines those with sensor visualizations, infrared, unaided, or night vision goggle visualizations to see what effect it has on detection time. And then finally, again, using the automatic vertical structure detection, how can we efficiently correlate that information with data which is already in the obstacle file to make it more of a living document? And then also to find the presence of power lines between these towers. Contributions are defining vertical obstacle challenge and simulation in the virtual environment. We also, in the course of that, benchmarked some existing clustering algorithms like dbScan and some three-dimensional correlation algorithms. We defined metrics that describe prevalence and prominence of underrepresented vertical obstacles, which are a tiny portion of these 3D point clouds. We evaluated the effectiveness of the graphical augmentations on notice time and the effectiveness of high fidelity sensor visualizations on obstacle notice time. For innovations, we show a new overlap algorithm, which finds vertical structures represented by sparse and cluttered point clouds. We also adapted a mesh filter process that quickly removes the vast majority of points which are not relevant for our task at hand. We introduced a new clustering approach, which uses vegetation's geometry to isolate tall protrusions. And we used a proportional height filter to distill vertical structure points when those points are nearly continuous. We also showed a method to efficiently correlate vertical structures into existing databases. And finally, a novel approach to find potentially hazardous wires. We're going to start with chapter 1, which is given a raw point cloud, how do we find vertical structures within the point cloud? So for backgrounds, finding poles in sensor data is not new. It's predominantly been done from the ground perspective. And there's also offline approaches predominantly from surveys and GIS. These offline approaches often have multiple requirements which don't apply to the airborne use case, such as coincidental data from other spectrums, such as a picture or video to supplement the three-dimensional data. They require uniform and dense point clouds, so over 100% coverage of the point of the area of interest. And then also other approaches, such as the ones at the right, the stacking pucks or the stacking boxes require that the user tune 5 to 6 specialized parameters for each one of the instances, which is not applicable or not very useful when in an airborne use case, you're going to have a variety of vertical structures from cell phone towers to power line towers. Online sensor data segmentation also has other shortcomings. Cameras require close range on the order of tens or hundreds of meters, multiple perspectives, such as the one on the right, where you see the same pole from the side, or high contrast backgrounds, not realistically cluttered and varied background like you'd see in the real world. And then many approaches have no tolerance for false returns with 3D sensors. So if a bird or a snowflake or a piece of dust causes a return for the 3D sensor, it will assume that that's an occupied area of space and will avoid it, even if it isn't. All right, our automatic vertical obstacle detection starts with a raw point cloud, applies a mesh filter to remove the terrain and low vegetation. Then it uses a sphere filter to detect and remove tall vegetation, which remains. Then if it's a continuous point cloud, it uses 3D connected component clustering and applies a proportional height filter to those clusters to isolate the structures which are likely to be vertical structures, or clusters which are likely to be vertical structures. If the point cloud is sparse and cluttered, not like this, where it's almost continuous, but when it's one like we simulate later on, we apply DB scan clustering and then our overlap filter to determine the presence of vertical structures. I'm going to start by talking about the mesh filter. So given a scene such as we see here with a distribution of points shown by these little gray squares, including these returns which are above the surface, which could be from birds or something like that. We start with a initial mesh, which is above the surface. The main variable here is the spacing between particles. That's what we're going to vary to maximize prevalence and density, as you'll see in results. After we build the mesh goes down until it either intersects with the plane or with the point cloud of the surface, or because of a neighbor which intersects, it stops going all the way to the surface because it has a simulated physical relationship with its neighbors. After that descent, the points which remain above the mesh, such as the red points above the towers, the red tops of the tree, or the red peaks of the roof, these are things which we're left to deal with. And in addition to these returns which are up here, which get passed through. We're going to start with showing how we deal with the vegetation protrusions, which is right here with a sphere filter. So the sphere filter uses Ransec sphere detection to detect the generally spherical arrangement of points which tend to be associated with vegetation. We double the radius of that sphere, and it generally encompasses those points which are not vertical structures. What this looks like with actual points in the process of our development, we have this tree. After we apply the mesh, you can see that a significant number of points still remain above the mesh. We detect that they have a generally spherical arrangement. And when we double the radius of the sphere, you can see that all those vegetation points are enveloped by the sphere. Next, we need to deal with the remaining clusters, and we're going to do that with the 3D connected component clustering and proportional height filter. What we're dealing with here are these typically long and wide surfaces, which may come from the peaks of roof or something like that. So the proportional height filter, we start with this set of 45 clusters. Each one of the clusters is characterized by its width, depth, and height. And we check for the hypotenuse, x squared plus y squared, square root of that, being less than the height, which is z. So this example on the left is an example of something that would not pass the proportional height filter because the hypotenuse is not bigger, or is bigger than the height in z. However, this yellow box here shows an example of potential vertical structure because the hypotenuse of x and y is obviously less than the height z of the box. Using the examples on the right, you can see we originally had 45, and after we applied this filter, 2 out of the 45 boxes pass through, and these 2 are actually associated with towers that you'll see in an example later on. If the point cloud is not very rich and dense, then we use sparse structures approach, which does DB scan clustering and overlap filter. Our overlap filter does initial clustering, then it characterizes the cluster. So here's an example of a red dot, which is a cluster on the in 3-dimensional space. We find the center and the radius of the points in that cluster. We do the same thing for a neighbor cluster. And then in the z-axis, we determine overlap when this bigger circle overlaps the bottom circle. These have approximately a 70% overlap. Another example of a cluster is this cluster, which is right above the larger cluster in the middle. You can see that it overlaps completely. So we associate these three clusters based on their overlap in the z-axis. And what's significant about this approach is that we tolerate noise and irregularities with fewer variables than other approaches. Really only three variables which are subject to less tuning. And with an actual point cloud, this is kind of what that approach looks like. This is an inverted tower, but you can see that this large disk here overlaps the small disk, which is below it, but these extraneous points do not actually overlap. So for results, many of the existing approaches, especially machine learning approaches, use the F1 score, which looks at overall precision and recall, relies on perfectly labeled data. However, we're prioritizing quickly finding points with the prominent poles, which are the minority of overall points. If we just maximize the point density with a really wide particle spacing, such as you see here, the mesh does not descend as far. Obviously, none of, or one or two of the points from the tree pass through, but not very many points from the tower pass through. And getting as much vertical structure points as possible is what we really need to do. So we miss all these points. So instead of maximizing this density, we introduced this metric called prevalence, which takes the density, the obstacle divided by the total, multiplies it by obstacle again to get prevalence, to prioritize getting a number of vertical structure points, not just increasing the density of vertical structure points, and allowing us to take care of these extra protrusions with our other processes. So what this looks like in results, this is a raw point cloud. You can see here, the orange are the vertical or poles actually. You can see that they're by far the smallest number of points in this tile, which contains over 10 million. After we apply our mesh, you can see that the poles protrude fairly clearly. Their original density is less than 0.2% with an original prevalence of less than 2,500 with a grid spacing of 8 meters, or particle spacing of 8 meters, is using the words that I was using previously. We increased the density almost 3,000% and increased prevalence, which is, as we talked about, a pretty good metric, close to 800%. So with another tile, which is doesn't have towers which are quite as prominent, you can see this is what we start with. Afterwards, the boxes which go through the proportional height filter, not all of them are towers, some of them are trees, but towers, the significant towers do pass, the prominent towers do pass through. You can see that we increase the prevalence from about 4,600 to over 35,000, which is a significant decrease. And then in a case where we have sparse and cluttered point clouds, there weren't open data sets that we could see on this. So we made our own in using AirSim in the Unreal Engine. We made 2 3D tower objects, and between those tower objects, we have floating orbs to simulate false returns that you would need to deal with in the real world. And we simulated a LiDAR right at the maximum distance, so that the tower on the left is within the LiDAR's maximum range, and the tower on the right side is right at the tip of the maximum range. So you can see that the point cloud from this tower on the right side is more sparse than what you would expect, or more sparse than the actual object. Using the raw dbScan clustering methodology, you can see that it over segments to over 80 individual clusters. It even over segments this tower in the foreground. When we optimize dbScan as much as we can by manually tuning it, we are able to successfully segment the tower on the left and the tower in the back, but we also erroneously associate these floating points to be part of the object, which they are not. Using the overlap algorithm though, however, we still accurately segment the tower in the front and the tower in the rear, but it eliminates these floating objects, which are between the two towers, which are clutter. And this example is case 4. You can see that the accuracy of overlap is 99%, which is an improvement over the other 2 approaches. So in summary for chapter 1, our mesh filter rapidly finds significant points, even when they're less than 2% of the typical scene. We have filters which remove the number of points that are remaining. And we have an overlap algorithm which consistently rejects false returns. Still remains a challenge to find occluded, less prominent towers, but we do find the most prominent ones. Moving to chapter 2, where we show graphic augmentation options and sensor visualization options to participants in a simulator. We started this work by doing a set of focus groups with current operators, civilian, military, engineers, technology, to answer the question of how challenging it was to detect vertical obstacles, what mitigations are out there, any shortcomings to the mitigations. So results that we saw, summarizing for time, we saw, or operators stated that they often have multiple competing tasks that are looking for visual attention and coping with high workload due to multitasking, such as this picture right here, which is from a video. He probably doesn't see that vertical structure there because he's looking over here while looking at his screens and who knows what on his heads-up display. It's especially hard to see obstacles at low altitude and cluttered displays and environments and integrated visual conditions. And one of the underlying challenges here is that database accuracy and completeness are either overestimated, which is very bad, or unknown, which is also bad. So for mitigations, there are multiple mitigations designed to improve obstacle detection by salience, expectancy, and value, but they do have shortcomings. One of the leading ones that people depend on or rely on is electronic flight bags and other aids, such as you see down here, like FlightAware. They're designed to reduce workload, but they have, to use them effectively, they really require background information about their shortcomings and limitations, which not a lot of users understands. And a lot of these mitigations, especially the technology-driven ones, rely on complete and up-to-date databases, which carefully consider the impact on busy operators. So here's an example of what showing some of those vertical structures is like on an area of Alabama. Not very usable, and also not very complete and not very accurate. Our final chapter, we'll try to tackle this a little bit. So for background, going into the simulator studies, we looked at the theories which would potentially inform what factors would be best to vary. The first theory that we looked at was guided search. It provides factors that affect search time for targets in a static scene, such as you see it right. So the advantage here is that it's a realistic visual scene with lots of variability. Unsurprisingly, the model says that salient features such as color, shape, motion across a large field of view affect how easy it is to see something. There's also a latest version of guided search 6.0, that offers 3 additional factors: priming, seeing guidance, and value, which we can go on later on if you want to talk about, that are somewhat equivalent to expectancy in the next model that we're going to talk about, which is noticing time, salience, expectancy, effort, and value. This theory predicts the likelihood and time to notice discrete events in a dynamic area of interest. So the difference here is that things are changing within these areas of interest, whether they're gauges or something, an object out the world. But the theory really looks at the factors of salience, expectancy, effort, and value in determining what the allocation of attention is going to be between these areas of interest and the effect that will have on noticing time. So the big takeaways that we took is for guided search and also for NTC, salience is a a big factor we wanted to look at. The other factor, using NTC's terminology, is expectancy, which is knowing there will be an object at a location. So those are the things that we chose to vary in our study. Our goal in this study was to evaluate effectiveness of various visual cueing schemes and vertical obstacle notice time in the low altitude flight environment. We had visualization factors to various salients. We had 3 levels. One was unaided. The next level was night vision goggles or infrared, the gray image. We had 3 levels of graphic augmentation designed to modify expectancy. We had 3 levels. One was no graphical augmentation. The next level was the circle. And the third level was a more precise bounding box around the obstacle. We had 22 U.S. Army Flight School students and graduates in a Black Hawk flight simulation where we used eye tracking, video, and audio to record the tower notice time for each participant. And we also had a side task of the participants listening to air traffic control radio and responding to their call sign. And this is what the eye tracking video would look like. You can see the yellow circle, which shows that there was a fixation at that point. And when the fixation coincided with the obstacle of interest, that determined the fixation time on the obstacle. A little bit more detail on the graphic augmentation. So the geometry and line thickness was based on a previous US government study. It hasn't been published yet, but the committee has a copy of the presentation and some related work that was published. We kept the line color constant to reduce the number of confounds. And this is exactly what the box looked like in the simulation. You can see the tower in the middle and the 4 lines around the bounding box. The same tower has the circle in the middle. In the actual simulation, the tower was either offset to the right or the left, but still within the circle, so that participants couldn't just look at the middle of the circle to find where the object was going to be. These pictures also do a good job of showing that this was a very rich visual environment where this tower wasn't the only thing to be looking for. There was lots of 3-dimensional objects they were flying through. Our route design had 6 5 to 7 minute coupled routes. In each route, the participant encountered 3 towers. 3 of these 4, the west, the north, the east, or the south. They were all the same 3-dimensional object placed in ecologically valid sites. And we also had sets of off-route vertical structures. So for day results, day was 1,000 foot ceiling, 3 statute mile visibility. The first route was unaided sensor visualization. And you can see the north tower had a box, east tower had the circle, south tower was unaugmented, west tower was not present on this route. For the reverse route, the visualization was infrared with the same augmentation for the same obstacles, just in reverse order. Our expectations were that obstacles would be noticed sooner or more reliably with the unaided video compared to IR, shown here, unaided first, then infrared. That obstacles augmented with the more precise bounding boxes would be seen sooner or more reliably than those with the circles, followed by those without cueing. So box within the tower, tower within the circle, unaugmented tower. And then for interaction, that symbology in the IR visualization would potentially be noticed before the unaided augmentation. So our results for daytime, there was no main effect of sensor visualization. Somewhat to our surprise, the unaided tower, unaugmented tower was actually seen before the tower within the box and the tower within the circle, and there was no interaction effect. And a little excerpt of what those results look like. The unaugmented tower, which is shown by the N here, was seen on average 28.7 seconds before. So on our y-axis, higher is better. This means they saw the tower much further from actually running from when it came into the rotor disc. While when it's down here, they saw it closer when it was coming into the rotor disc. Comparing the unaugmented tower to the tower within the circle, you can see that this was significantly faster. The unaugmented tower was also significantly faster than the box within, or the tower within the box. For dusk, dusk was 700-foot ceiling, 2 statute mile visibility. The first route was unaided. You can see how the clouds were lower, the visibility was lower, it's a little bit darker. Same visualization or same graphic augmentation options, just in different order on different towers. And then for the second route, we had infrared, same graphical augmentation options in reverse order. We had the same expectations that I just talked about. In this case, though, because we had the reduced visibility, towers within circle were actually noticed prior to unaugmented towers, and towers within boxes were noticed after unaugmented towers. There were no significant effects for the other 2 expectations. Another excerpt from those results is you can see that the unaugmented towers were seen after towers within a circle here. However, the towers within the boxes shown by BT were seen after unaugmented towers. Then for night conditions and expectations, night we returned to 1,000-foot ceiling, 3 statute mile visibility. In this case, unaided sensor visualization did not make sense because it was just it was nighttime and it would be black. So we replaced unaided with the night vision goggle sensor and compared that with IR with the same graphical augmentation or graphic augmentation options on 3 of the 4 towers. Similar to day, unaugmented towers are actually seen before towers within the circle and towers within the boxes. And you can see here that the unaugmented tower, unsurprisingly, was seen, or as we talked about in the previous table, was seen before towers within the circles and towers within the boxes. Observant audience members may notice that we also had these graphical detection times out here. Although it was not when the participant noticed the tower, we did also record when the participants noticed the graphics, which typically preceded them saying the tower was within the graphic. And that's something we're going to talk about later on. So we also did qualitative post-flight surveys. In daytime conditions, participants said that they had a slight preference for unaided over IR visualization. In dusk, they had a strong preference for IR over unaided. Recall that both of these sensor visualizations really had no main effect on detection time. At night, they reported a strong preference for MVG over IR. And our data, although we didn't show it in a graph due to time, showed that actually detection time was slightly faster with MVG over IR detections for sensors. For the graphic augmentation options, box versus circle, participants reported that the box possessed most useful information. So 73% said it was the most useful information quality, best alignment with the towers, and most useful for finding obstacles. And this is obviously interesting because their time of detecting the tower within the box actually lagged behind the other detection options. So summarizing this study, all except for 1 tower due to a simulator issue were noticed before entering the rotor disk with a wide variation in detection times. Sensor visualization only affected detection time during the night ambient visualization condition where the MVG was faster than the IR. Overall, this shows that altering the scene salience has low effect on detecting the subtle towers, probably due to their low cross section. The boxes, which were designed to highlight tower position, tended to obscure the hazard itself. Participants' preference for expectancy and precision, though, may have outweighed the masking because they obviously preferred the box graphic augmentation. There was also the fastest detection time for towers within the circle during dusk. This shows that the less precise graphic may be more effective despite the pilot preference for the box. And our distinction between box and circle notice time, even though they had a big difference in precision, was less pronounced than anticipated. And the box and circle detection foreshadows potential for fixation, which can erode situational awareness if these are false positives, which we'll talk about in future work. All right, for the final chapter, Given that we have this vertical structure information, how can we try to fix the database which underlies a lot of these graphic augmentations and mitigations which exist nowadays? And how can we infer the presence of power lines? So current feature matching approaches that do manual updating of new entries, such as DOF and geo packages. It's good that they supplement the existing objects. However, new entries have to be manually updated, which is obviously an onerous task. Approaches such as 2D protection, 2D projection, or predictive mapping are good that they're automatic. However, they overwrite the existing objects, so they don't actually take the previous information into account. We are going to be working in the Federal Aviation Administration's digital obstacle file, which is updated every 56 days. It's designed to depict hazards to aerial flight. It really focuses on obstacles which are greater than 499 feet above ground level, and it gets lower within 3 miles of airports with instruments approaches, such as the Detroit Airport, where you can see there's many hundreds of obstacles down to taxiway lights, in contrast to Ann Arbor, where, except for the airport to the south, there's really only tens of things which are in the database. It's noteworthy that of the 500,000 records which are in DOF, which don't necessarily include all obstacles, 56 have a significant horizontal error greater than 250 feet, as you can see here for the distribution. And the study that we're going to, our results are going to be focusing on Delaware's DOF, which has this height distribution of vertical structures. You can see that most of them are less than 400 feet with 1 to 1,000 foot obstacle, but the majority of them are relatively short. So power line detection, how is that done now? It really is framed by the challenge that at 800 meters, a high tension power line only occupies 0.0015 degrees in the field of view. So physically, with an eyeball or with a detector, there's just not a lot of cross section to detect. Recent methods either rely on close range on the order of tens of meters, as you see here, continuous contact, so starting with contact and keeping contact, or establishing the tower purpose, as you see here. So if you know the tower is a power line, or it supports power lines, then you can estimate where the power lines are going to be within the towers. That works if you have a perfect database and know where it is, but at that point you already have the information. So what happens if you don't know? That's where a vertical, or we start by having a good database updating approach, which starts by having a index hash table that appends each one of the existing DOF entries with a spatial hash key. Based on that index hash table IHT, we build an uncertainty hash table based on to discretize the horizontal uncertainty. Then, using an approach such as what we showed in chapter 2 of the vertical structure detection, we query that uncertainty hash table to see if it's in the database, in that hash table. If it isn't, then we add the entry. If it is, we determine if it's similar to an existing index hash table entry. If it is not similar, then it gets added as a new entry. If it is similar to an IHT entry, we automatically update the position and update the accuracy of the entry and feed back into our index hash table, which could be fed back into a vertical structure database. So our spatial hash discretizes position with a 1/4 of a second resolution. We chose 1/4 of a second because that's about 25 feet latitude, anywhere from 19 to 24 feet longitude based on how far away you are from the equator. That gives us a box that's less than 25 by 25 feet. And we chose this because the highest horizontal accuracy that we have is a 20 foot, which a 20 foot radius circle encompasses a 25 by 25 foot box. I might have said meters, I meant to say feet. We start by, our first step is building the spatial hash or building the index hash table by appending each one of these existing entries in DOF with a corresponding spatial hash. That hash takes the degrees, minutes, seconds, rounded to the nearest quarter second. We're only applicable at this point to a hemisphere. So we remove the north or the west, north, south, east, or west. Same thing for longitude, where we take degrees, minutes, and seconds rounded to the nearest degree. And that gives us this string of digits, which gives us a unique identifier for all these rectangles within the hemisphere. While I have this slide up, I also want to point out that this is the information that DOF has, and what we're leveraging in addition to the position is also the date of observation, the horizontal and vertical accuracy, which are shown by these numeric and letter codes. So next is building our uncertainty hash table. Why do we have to do it? Because an exhaustive nearest neighbor search will cause incorrect associations. So if we observe this orange tower in the center, how do we know if it's the green or the blue or a tower of its own? Nearest neighbor would say it's probably this one because it's closer, even though the height may be different. And it takes a while. So it could be incorrect and it takes a while. The horizontal uncertainty of these two towers could easily overlap. So again, that doesn't really tell us which tower it could be associated with. So what we do is we discretize the uncertainty. Each one of these green and blue circles, which represent the horizontal uncertainty, we overlap those with an array of these cells, which have a little bit of padding, and you can see the width of the circles are wider because we don't exactly show the center. The center is actually represented by this rectangle. And what that looks like in the uncertainty hash table is if you get an observation which is in the center of the green circle, that green circle sends you to the value of the same spatial hash because that is the index in the index hash table, the center of that obstacle. Same thing for the blue tower on the right. If you got an observation at the center, that would send you to the index. But if you have this red observation, which is along the outside of the green tower, that also sends you or has a corresponding value of the center and rapidly and efficiently tells you in the index table where to look for corresponding values. An interesting case that we're going to deal with, though, is what if you have an observation like the orange tower, which you've been looking at, which is between the two towers and encompasses both the tower on the left and tower on the right. How can we quickly say we need to be checking for this tower and for this tower? This would be the corresponding value for this cell because it encompasses the tower on the right and the tower on the left. You can see the blue tower spatial hash and the green tower spatial hash. So going back to the tower perspective, how do we determine which one it should be associated with now that we've established the orange towers within the area of uncertainty? The green tower, again, is the spatial hash. The blue tower is the one on the right. We start by comparing or we do it based on determining similar height. So the green tower, which is an existing observation, we pad that with a height uncertainty, which is in the DOF that we talked about. And if the observation height is within the bounds of the existing tower, then we determine that that's a similar tower. Now that we've determined it's a similar tower, we can update position. And we don't update position just based on saying the newest observation is the best. We also take into account the age of the observation, like I pointed out. So if we have an observation here, the orange observation, which is relatively current, only 1 year old versus a 4-year-old prior observation, our updated position is a little bit closer to the newer observation, but still takes into account the previous observation. Okay, so for power line inference, instead of trying to detect the power lines directly, we're trying to take advantage of the relative detectability of towers, which tend to have a much higher cross section, and also that wires tend to be supported by towers. We determine this based on height, proximity, and arrangement. So given this set of 3 towers on the right side, height of tower 1 is h1, height of tower 2 is h2, height of tower 3 is h3. Distance between tower 1 and 2 is distance 1, 2. Distance between tower 2 and 3 is distance 2, 3. We assemble sets of vertical structures that are greater than or equal, that have greater than or equal to 3 towers. We determine similar height above the ground level based on a maximum height buffer, alpha, which is the maximum height of the 3 towers minus the minimum height of the 3 towers. We also determine that they are similar if they have spacing which is less than a maximum horizontal spacing proportional to height. This height distance ratio, nu, is the maximum distance between the towers divided by the minimum height. And we do this because there's a tendency for power line towers to have proportional height and not have a huge variance in their height versus the span of the power lines they're supporting. In order to make our inference method a little bit more accurate, we also do a subsequent more restrictive filter when tower sets are not aligned as much in a straight line. And alignment is where this interior angle between 3 towers in the results is less than 184 degrees. So if towers are within 4 degrees alignment, we allow a less restrictive height distance and height maximum height buffer. But when they're less aligned, we have a more restrictive maximum set height difference and maximum set height distance ratio. So going into results for database updating, the original Delaware DOF had 1,063 entries with an average horizontal uncertainty of 206 feet. This is how those horizontal uncertainties were binned. You can see the vast majority of them are in the 250-foot bin. After we correlated with the National Geospatial Intelligence Agency's digital vertical obstacle file, 719 of those entries were updated to more precise horizontal accuracies and positions. You can see here that there's a lot smaller number of 250-foot horizontal accuracy and a lot more shown by the orange of 50-foot or 20-foot horizontal accuracies. These are bins again. So this just shows the most. So 50-foot actually includes everything from 21 all the way up to 50-foot horizontal uncertainty. After we do our database updating method, we show that the average horizontal inaccuracy for the Delaware DOF reduces to 56 feet. In the process of doing our analysis, we actually found that there were some false negatives, what we're calling isolation. For example, this tower in the middle in green was in the database, but for some reason the tower, which is just as prominent, same height, was not in the database. So our analysis ignores these isolated towers because a tower on its own does not support a power line. But if we had the benefit of our actual vertical structure detection, we would easily detect the towers, which are its neighbors, and this would be an easy thing to infer. There were other examples of a cell phone tower on top of a 20-foot power line tower, which was erroneously shown as a transmission line when the transmission line shown in red was only 20 feet AGL. And there's other examples that I can go through later if you're interested. So results for power line inference, our overall goal is to avoid false negatives. That's where if you're flying along or if you're trying to detect the power, it tells you that a power line is not there when it is actually there. That's something that is very bad that we want to avoid. Something that we are willing to tolerate is minimizing false positives. Those are where it will tell you a power line is present when it may actually not be present. So we started by examining the height above the ground level, the maximum height buffer alpha, and the maximum horizontal spacing proportional to height. That gave us these results. Again, false negatives is on the z-axis here. We needed to keep 0% false negatives and minimizing the false positives for corresponding height buffers and height distance ratios. And the minimum false positives was here, just under 15% false positives with 0%, while maintaining 0% false negatives, and that was with a height distance ratio of 9 and a height buffer of 85 feet. Implementing our subsequent filtering for the less aligned towers using an alignment that was, if they were less aligned than 4 degrees, this was the minimum false negatives. So maintaining 0% false negatives while minimizing false positives gave us 12.96% false positive rate. So a slight reduction while maintaining 0% false negatives. So summarizing chapter 3, our database decreased the horizontal uncertainty from 206 to 56 feet. It's interesting to note that more than 30% of our digital vertical obstacle file did not correspond to the FAA's digital obstacle file, showing that both databases have room for improvement. And our power line inference method found all transmission line towers that were not isolated with 0% false negatives and 13% false positives. So in conclusion, we presented a vertical structure detection that can find prominent towers in rich and sparse point clouds, rapidly distills irrelevant points from a scene. The overlap algorithm consistently rejects false returns in sparse and cluttered point clouds. We ran focus groups, which confirmed unexpected obstacles continued to be a threat. Simulator studies showed that participants had a wide range of tower detection times. Changing the scene salience with a sensor usually was insignificant, but graphic augmentation did draw attention, but did not result in faster tower detection. Boxes were detected soonest, as you saw in the graphs, but they also tended to occlude the actual tower object, making tower detection a little bit later. Towers within circles are seen faster than towers within boxes, indicating utility of the less precise queuing as long as it's somewhat accurate. The current obstacle databases are incomplete and inaccurate, so we introduced this vertical structure correlation method to provide efficient updates. Detecting and avoiding wires requires directly detecting the wires, so we did a power line inference method which finds wires at ranges where seeing or sensing is difficult. And then an overall conclusion, obstacle detection is strongly affected by expectancy. That's what we saw in our simulator study. So this work shows ways to increase awareness that can also apply to automated obstacle avoidance by increasing expectancy with sensor-informed graphic augmentations, sensor or database-informed augmentations. There's an opportunity for a lot of future work here. The data set, which we didn't really have time to describe, was from a nadir looking down perspective with heavy coverage. Sideways perspective would be much more representative of an airborne sensor. Expanding the application of power line inference to rolling terrain. So Delaware is obviously not the most mountainous state. Hopefully our method that looks at AGL height of the tower, above ground level height of the tower, would apply, but we didn't have time to apply that to a different setting. If we did further analysis of the tower false positive, that might actually reveal effectiveness of the power line finding algorithm. And I would suspect that a lot of the false positives may actually be legitimate power line presences that were not correctly labeled in the database, but that's work that could be done. Next steps could obviously be combining the modules into one architecture, using this more representative perspective. Future human subjects research could incorporate augmentations that are not as accurate, so all of our graphic augmentations actually had obstacles. We could also widen the variety of circle radii to determine if less horizontal accuracy, because they all had the same horizontal accuracy, if that affects the truss, detection rate, or detection time. The graphic augmentation design was simplified from the previous study to reduce the number of confounds, but the tendency for the box to mask the tower shows that reducing the line thickness or brightness could reduce the tendency to mask obstacles and potentially result in faster detection time. We could also have gaze-based graphics that could be fading in and out when an object of interest is in the central field of view, since we know where a participant is looking. Although our simulation had really good visualization and cockpit interfaces and was immersive, there's no substitute for flight evaluations in actual aircraft. We could have had faster ground speed, steeper turns, more engaging workload, and jet task. So finally, I'll start by acknowledging my family, who is at the Space and Rocket Center right now. That's why it's so quiet. They've been very patient with me disappearing into the office, and I'm very thankful for that. In roughly chronological order for people who've helped me get where I am, I want to thank what I'm calling trailblazers. These are people who were other active duty officers who embarked on the journey of doing advanced research and gave me a lot of very helpful advice in addition to just blazing the trail. When I got lined up with a West Point utilization, they were incredibly helpful and also incredibly gracious when some other opportunities arose. And I'm incredibly thankful for the help that you provided and continue to provide. Don't have enough time to go into details for how thankful I am for my advisors. Cannot say enough great things about you, but I'm also short on time. But you are.
I think that's a good place to stop.
And it wasn't just faculty and trailblazers, but classmates who were 10 or 20 years younger than me were helpful. Kevin, Aaliyah, Emma, Shervon. The list could go on and on, but graduate school is a team effort, and that's what helped me survive to get through the coursework and get where I am now. And lastly, I want to thank my co-authors, Joey Drockton, Bob Copeland, Mike Wilson, who went above and beyond just being, friends and advisors, but also really helped me write some papers and add to the body of research. So I want to thank them as well. I look forward to your questions. Thank you for your time.